So how old are stars? Obviously if stars are old, then it's a huge problem for the creationist model, which puts the age of the universe at 10,000 years or less. Well, we know that stars are very much older than that. So just for information, how old can stars get? Well, our own star, the Sun, is around 4.5 billion years old. We know it's probably roughly halfway through its own life, maybe a little bit less. There are many stars of the same age as the Sun in the Milky Way, and there are many much older and much younger. There are still stars being formed, like the Pleiades that we saw in a previous slide, and there are some stars that formed roughly when a galaxy formed, which is maybe more than 10 billion years ago. Stellar ages vary enormously. The life of a massive star may only last a few tens of millions of years for the largest. But for smaller stars, even smaller than our Sun, they can live tens, maybe even hundreds of billions of years. Well, how do we know with so much confidence these enormous ages? It was thought for some time that the Sun was just cooling down from its initial heat in the formation of the solar system. This is not true. The Sun is generating heat in its core by the process of nuclear fusion. Nuclear fusion is very well understood. It's similar to the process that goes on in nuclear power plants. That's nuclear fission. In nuclear fission, large nuclei, like uranium, are split into smaller nuclei with the release of energy. In nuclear fusion, very small nuclei like hydrogen, helium, lithium are fused together under enormous temperatures, and this process also releases more energy than was put in. We can create fusion reactions on Earth, not particularly long fusion reactions, maybe a few fractions of a second. There are projects which are aiming to create sustainable nuclear fusion power plants. This is the ideal solution for our power needs as the human race becomes more and more power hungry. Nuclear fusion is very safe, it creates no dangerous byproducts, and there's a huge supply of fuel just in the ocean. What about the Sun? How could we estimate roughly how long it's going to live? Well, we know the Sun's size, so we know exactly how much fuel there is for the process of nuclear fusion. We also know how rapidly it's burning that fuel. Because we can see exactly how bright it is, we can measure how much energy the Sun is giving off in total. And we know roughly how efficient nuclear fusion is. We can combine all of this knowledge together, the amount of fuel the Sun has, the amount of energy it's creating, and the efficiency of nuclear fusion, to tell us roughly how long the fuel in the Sun will last. And that gives us a number of about 10 billion years. Simulations which aim to simulate the exact processes that are taking place inside the Sun and therefore get a much more accurate estimate come up with a very similar figure. Isochrones are graphs which represent the way a star should look depending on its mass at a fixed age. The word isochrone comes from the Greek words meaning same time or same age. They're based on computational models which take into account the amount of heavy metals in a star. On the left of this slide you can see isochrones which show how stars look at ages of 100 million, 1 billion and 10 billion years old. What do I mean when I say you can see how stars look? This is a colour luminosity diagram, and it's very frequently used in astrophysics. On the horizontal axis is the star's colour, which correlates very well with temperature. Hotter stars are more blue, whereas cooler stars are more red. On the vertical axis you can see the star's luminosity, or absolute brightness. There are many variations of this plot, but essentially they all show the same two properties. To help understand the lines on the diagram, you see they all run from the lower right corner of the plot, run up and towards the left, and then diverge in various ways. The line of an isochrone is parameterized by mass. That means as you follow the line, the mass goes from very low to very high. In an earlier slide I explained how high mass stars evolve much more quickly than low mass stars. In the isochrones, the lower mass stars are the ones at the bottom right hand corner. As we follow the line up to the left, we trace a route known as the main sequence, where almost all stars are to be found. This is a period of a star's life that takes the most time, where it's burning hydrogen to helium stably in its core. That's about as much detail as I need to go into in this diagram. Suffice to say, we can create these isochrone curves entirely in theoretical models on computers. When we then lay them on top of actual observations of colour and luminosity of actual stars, such as I've shown in the diagram on the right, you can see that they line up beautifully. This is a set of observations of stars in the very large globular cluster 47 Tucano within our own galaxy. The axes are slightly more complicated here, but essentially they're colour on the x-axis and luminosity on the y-axis, just like before. The isochrones plotted here are for stars with the metal enrichment measured for this particular cluster and ages between 8 and 16 billion years. As you can see, the stars in the cluster lie very nicely under the isochrones for about 12 billion years. This is exactly as we'd expect. This is roughly the age of the galaxy, and this globular cluster was expected to have been formed right at the very beginning of our galaxy. Also, globular clusters form almost exactly at the same time, so all the stars should have roughly the same age. There is some scatter, of course, partly due to the fact that the stars didn't quite form at the same time, and also due to the error in our observational methods. But the fit is still remarkable. This one creationist claim is a masterpiece of anomaly hunting. Again, rather than look at the big picture and attempt to explain away the undeniable evidence head on, Kent Hovind picks out a very specific anecdotal argument regarding the star Sirius. The aim is clear: to make it look like astronomers don't even know how to predict the most straightforward of stellar phenomena, and to suggest that the models on which we rely are completely incorrect. The story here is that a few second-century sources claim that the star Sirius, the brightest star in the sky after our own sun, used to be red in colour. Currently it's a pale bluish-white. The possibility that Sirius might have been red at some time in the very recent past would seem to cast doubt on our models of stellar evolution, but of course Hovind claims it as evidence that things in astronomy change very much faster than we think they do. Of course, the story is certainly an error. There are many sources of Sirius dating from the time, especially from the Chinese astronomers, who never mention it as anything other than white. Other European astronomers, in fact the majority, also describe it as white or pale blue and never anything different. Sirius was a very important star for the ancient Egyptians, associated with their goddess Isis, whose colours were white, blue and gold. So why did a few second-century astronomers think Sirius was red? We may never know. It certainly looks red from some locations on Earth when it's near the horizon because of atmospheric dust. Also, the translations of Ptolemy's work are dubious at best. One thing is for sure: Sirius was not a red star in the last 2,000 years. For a start, this phase would have resulted in the ejection of a large amount of gas from the star, which we would be able to see around the star today, and we can't. And also, if stars change so rapidly, we'd be seeing them change in the skies today, but of course we don't. There are quite a few examples in Hovind's slides of anomalies like this. Often when dealing with anecdotes, it's impossible to know the truth for sure because we're just dealing with reported speech. We really don't know what actually caused Ptolemy to write about a red Sirius, but we do know, thanks to a great many other sources, that Sirius was never red. And we know that anecdotes have no place in science. There are several other smaller claims that Hovind makes about astronomy that are fairly quickly cleared up just by reading into the subject a tiny bit. Again, the common creationist tactic is to read just as much and just as deeply as they need to in order to reach the conclusion that they want to reach. Then they don't bother looking any further. This first issue is about comets. We know that comets are fairly fragile. They're basically giant dirty snowballs hurtling through space. When they get near the sun, they begin to boil away because of the heat. Because of this, comets should have a lifetime of around 10–20,000 years. But the models expect them to have been formed in the early years of the solar system, so they should be billions of years old. So why are they still here? This one is easily cleared up. Comets come from a region of space known as the Kuiper Belt, which is a reservoir of objects at the very edge of the solar system. This is far enough away from the sun that the comets can live there stably for a very long time, but occasionally they get nudged off their orbits by a chance encounter with either a minor planet or another comet. When this happens, they can get kicked into orbits that instead take them towards the inner solar system, where we see them as comets. Once this happens, then they usually last the 10 to 20,000 years predicted. The Kuiper Belt objects have been directly observed, of course, to prove the point, so there is no problem here whatsoever. Further out still is a zone known as the Oort Cloud, named after the famous Dutch astronomer Jan Hendrik Oort in 1950. This has never been directly observed in full, though there is reasonably good evidence that such a region exists a little under a light year away from our star, and there are 4 plausible candidate members that have been imaged by powerful telescopes. Whereas the Kuiper Belt is the reservoir of short-period comets, the Oort Cloud is the reservoir for longer-period comets such as Halley's Comet, which has an orbital period of 75 or 76 years. The reason for assuming the existence of such a zone is simply that the orbits of a large fraction of long-period comets have an aphelion, or furthest distance from the Sun, of around 50,000 astronomical units. That's 50,000 times the distance between the Earth and the Sun, which is this distance of slightly under a light year. It is likely that this spherical cloud of objects is a direct remnant of the outer edges of the protostellar disk that formed as our solar system was in its infancy. Creationists claim that such a cloud doesn't exist, though their rationale here isn't very clear. Perhaps they merely mean to cast doubt on astronomy in general. Either way, the Oort Cloud isn't a particularly important part of astronomy, though the evidence for it is reasonable, and it seems sensible to assume that it does exist, based on the evidence that we have.